I am going to start with water treatment. I don't know where I stopped the last time. Does anyone remember?
Ma'am, I think you taught them hardness.
I finished hardness.
Yeah, I think so.
Did I come to alkalinity and softening?
I don't think they were taught that. There was Chick's law and there was hardness of water, and then you gave them numericals, I guess. Ma'am, let me check the previous recording.
If you have it, yeah, please check. Just give me the slide number, Anuja.
Yes, ma'am.
What's the slide number?
Ma'am, till slide number 29.
29. So up to Chick's law. And then I said
Yes.
something about hardness, or I dropped it?
You dropped it there.
I dropped it at 29.
Yes, ma'am. And then gave them numericals.
Okay, great. Thank you.
Okay.
Okay, so we'll continue with where we stopped last time, and I finished talking about disinfection. So now we'll tackle another topic in water treatment. Now, I've already mentioned in the previous class that in groundwater, a very frequent problem is hardness. And hardness is due to the presence of two cations. So we have calcium and magnesium, and the concentration of the two ions together is called hardness. Now, we also know that hardness is these two ions, let me say it in another way. Calcium and magnesium are cations, they're divalent cations, and they are non-toxic. They are micronutrients, macro or micro, it depends on the organism. They can be either micro or macronutrients. In either case, they are non-toxic, and they are essential. So that is not the issue in this case. The issue here is twofold. One is what is called the formation of soap curd. So when you wash your hands with water, sometimes you notice that you get this whitish curd like precipitate when you use soap, and there is no foaming, no frothing, which is essential for cleaning. So this formation of soap curd happens when the hardness level of the water is high, and it increases the soap requirement, and it also causes difficulty and lack of efficiency in cleaning activities. The second issue is heating. When you use water heating appliances, so it may be your water heater for bathing, it may be your steam iron, which uses water for generating steam. There are so many other home appliances which use water, and the heating element is in contact with water. So if you're using hard water, a scale will form on the surface of the heating element. Your electric kettle is another one. So a scale will form over a period of time, maybe over a year or two, depending on how much hardness there is in the water. You will get a whitish scale on the surface. This scale can be removed with a dilute acid, and if you are unable to remove it, it will cause reduced efficiency of the heating element, and under severe conditions, it can even result in failure of the appliance, okay, the heating appliance or whatever it is that you're using. And this is mainly, the scale has basically two compounds, calcium carbonate and magnesium hydroxide. So these are the two major issues related to hardness. Are you able to hear me?
Yes, ma'am. You're clear.
Yeah, okay. Uh, Okay, so there are two major issues, like I said, that are related to hardness. One is the formation of soap curd, and the other is the formation of scale on the heating element. Now, you can use synthetic detergents that will reduce the problem, but that will not eliminate the problem. We do have standards. We have water quality standards for hardness. The general level of acceptance is less than equal to 200 milligrams per liter as calcium carbonate. Let's look at something else. Now, this is a bar graph from the Masters and Eller textbook. And what it shows you is a way of presenting It shows you a way of presenting the concentrations of cations and anions in a bar diagram. So on the top, you can see the cations, and on the bottom, you can see the anions. The scale is ion concentration in terms of milligrams per liter as calcium carbonate. Now, notice what we said is the definition of total hardness. Total hardness has no other definition except the concentration of calcium 2 plus and magnesium 2 plus. Okay, so that is total hardness. Now you notice that these cations have to be associated with some anions, right? Now there are many anions in this particular water. There is bicarbonate, there's sulfate, there's chloride. You also have other cations. You have sodium, potassium, and so on. Now, there are a few things that we need to remember. Carbonate hardness has two forms. You can have CO3 2 minus, or you may have bicarbonate, which is HCO3 minus. Now, in most waters, you will find that the bicarbonate dominates, because otherwise we won't be drinking it. You need very alkaline waters to have substantial amounts of carbonate. In bicarbonate, for the waters that we are generally dealing with, bicarbonate dominates. So that is what we call carbonate hardness. So this part of the hardness, so the hardness here is calcium plus magnesium. Carbonate hardness is the hardness associated with carbonate or bicarbonate. In our particular example here, there is no carbonate, and therefore it's just bicarbonate hardness. So, oops. So due to anions like carbonates and bicarbonates, we have carbonate hardness. This is called temporary hardness because it can be precipitated by boiling. Now, you can see the total hardness is much greater than the carbonate hardness. So what is the remaining hardness called? The remaining hardness from an anion perspective is the total hardness minus carbonate hardness. So that will give you non-carbonate hardness. So in this case, we will have 323 milligrams per liter as CaCO3. That will be our total hardness. You have to subtract carbonate hardness, which is 135.2 milligrams per liter as calcium carbonate, and the remaining, not sulfate, the remaining will be called non-carbonate hardness. And you can say that that non-carbonate hardness is associated either with sulfate or chloride. It can be associated with anything. And I can draw this bar diagram by replacing calcium. I can draw this bar diagram by putting chloride here and sulfate here. It doesn't matter. Okay, so it's not that they are joined together as salts. They are not. They are all dissociated as cations and anions. So that's the definition. Okay, so total hardness is equal to carbonate hardness and non-carbonate hardness. That is a simplistic thing. There can be exceptions where you can have a situation where the bicarbonate concentration is so high, it may be higher than the total hardness. So in that case, your total hardness is defined, remember, by calcium and magnesium and nothing else, and your carbonate hardness will be greater than total hardness. So that can happen. That is possible. Now, remember that hard water is not suitable. It's not suitable for drinking, even it tastes bad. So it has a brackish taste to it. And also, like I said, it's non-toxic. So toxicity is not an issue. What is an issue is a commercial impact. So you have the soap problem, the cleaning problem, and you have the scale formation. So these are the two issues related to hardness. Now, based on hardness levels, we can classify waters as soft water, moderately hard, hard, and very hard water. Now, if you notice, you can express it in terms of milligrams per liter as calcium carbonate, which is very common. That's the most common way of expressing it. The other way of expressing it is in milliequivalents per liter. And milliequivalents make it very easy because in terms of charge, remember every solution has to be electroneutral. So if it is electroneutral, then the milliequivalents of the cations are equal to the milliequivalents of the anions. So that works out. Or if you have milligrams per liter as CaCO3, that also works out. So it has to be a uniform scale that can be applied to all cations and anions. So hardness in terms of milliequivalents, if it is less than 1 milliequivalent, that in terms of milligrams per liter as CaCO3, this is as CaCO3, will be less than 50 to 75. Then moderately hard will be 1 to 3, which can be 50 to 150. Hard is 3 to 6 milliequivalents per liter, and that will be hardness level of 150 to 300 milligrams per liter as CaCO3. And very hard waters are greater than 6 milliequivalents per liter and greater than 300 milligrams per liter as CaCO3. So total hardness, according to the water quality standards for drinking water, should be less than 200 milligrams per liter as CaCO3. If no other good quality drinking water is available, then you can tolerate acceptable limit is 600 milligrams per liter as CaCO3. Then we come to alkalinity. Now, alkalinity is another important parameter, which is a measure of the water's ability to absorb hydrogen ions without resulting in significant pH change. So it provides a buffering capacity for the water. And this is especially important when you think about coagulation. Now, what happens in coagulation is when you add alum to water, if there is no alkalinity, what will happen? Alum is aluminum sulfate. It will form aluminum hydroxide and the sulfate will combine with the protons in water and you will have acidic conditions. If there is alkalinity in the water, that will provide a buffering capacity. So as long as there is sufficient alkalinity in the water, that sulfuric acid will not form and you will get a buffering of the pH. Okay, so total alkalinity less than 200 milligrams per liter as CaCO3 is required to ensure that there is no change in pH and we want a neutral pH. Now let's come to how do we deal with hard water. So now that we have identified, we know the standards, we know how to deal with, how to measure the hardness of water. What do we do if the water is hard? In general, surface waters are not as hard as groundwaters. I've already mentioned to you, groundwaters tend to be in contact with carbonate rocks, and because they are in contact with rocks containing carbonates and bicarbonates, that's why they tend to be harder than surface water. So I've already mentioned all these points. And softening is required when the hardness level is greater than 1000 milligrams per liter as CaCO3. There are two options. One is called the lime and soda option, and the second is ion exchange. So the oldest method for softening water is lime and soda. It gives crude levels of removal. It's like alum. It gives you very crude efficiency, but it's good enough to meet drinking water standards, and it is really, really cheap. Okay, so lime and soda is the most common, I would say the most common and the most popular option for softening hard water. The other option, ion exchange, is useful when you have finer applications. Let's say your application is not drinking water, but maybe the manufacture of pharmaceuticals or the manufacture of other fine products where you have a requirement for, let's say, zero cations and anions. So in those cases, you may go for ion exchange. Because it's based on synthetic or natural materials for adsorption, it's very expensive, but the level in the lime and soda process is 30 to 40 milligrams per liter of CaCO3. So that is the limit. The practical limit of the process is 30 to 40 milligrams per liter of CaCO3. In ion exchange, you can go further down. Let's say you want to go to practically zero. Okay, so if you want to go down to that level, you cannot do it with lime and soda. You have to rely on ion exchange. So let's take lime and soda. Let's take that first. What you can do is you can add quicklime. Quicklime is CaO, calcium oxide, or hydrated lime. So when you add quicklime to water, it will form the hydrated salt. So you will get calcium hydroxide, CaOH twice. So this is, you can add it either in solid form, this is a solid, or you can add it in the liquid form, the hydrated lime form. Okay, in either case, you get the same result. What will happen is that carbonates of calcium will form. So CaCO3 has very, very poor solubility. And this poor solubility means that they will precipitate out of solution. If I remember right, the solubility of CaCO3 is 15 milligrams per liter in water. Is it 15 or 25? Yeah. Let me check. Um, Yeah, so the solubility limit for calcium carbonate is 15 milligrams per liter at 0 degree centigrade. That's for sure. And the practical limit is 30 to 40 milligrams per liter of CaCO3. So this precipitates out of solution. And if you have significant amounts of magnesium, so now let's imagine that we have a water which has 100 milligrams per liter of calcium and 20 milligrams per liter of magnesium. That's very common. Now, if I can bring calcium out of solution, if that comes down to, let's say, 40 milligrams per liter, I don't really need to remove magnesium. So in general, just the removal of calcium carbonate is sufficient. You don't need to go for magnesium removal. For the simple reason, if I want to remove magnesium, I have to increase the pH more than 11 because it will not precipitate under neutral conditions. The hydroxide concentration has to be much higher, which means pH has to be very high. It has to be greater than 11. Excess lime has to be added for it. So very often you ignore that because you can meet the standards without removing magnesium. Okay. So you can bring the hardness down to 30 to 40 milligrams per liter of CaCO3 simply by removing calcium carbonate from solution. However, if you have the reverse case where the magnesium concentration is higher than calcium, then obviously you have to do this third point. You have to take care of this and increase the pH, then bring it down again. So you first increase the pH, excess lime is added, magnesium hydroxide is removed along with calcium carbonate, and then you have to re-neutralize or recarbonate the solution. So recarbonation of the solution means you add CO2 to it to redissolve these calcium carbonate precipitates. So this is in a nutshell. Then we go for the finer process. I've already mentioned that if you want to achieve less than this level, 30 to 40 milligrams per liter of CaCO3, if you want to go below that, then you have to go for ion exchange. Ion exchange is a type of adsorption process. And what is adsorption? I'm not going to go too far except to say that, let me see. So adsorption is a process, if you can imagine that you have porous rock-like material like this. This is a porous material. This is a natural zeolite, and you can see the crystal structure. The crystal structure has pores in it. And the molecular structure, the crystal structure itself is porous, and the rock also is porous. So it has very, very high surface area. Now, what happens is, let us say you have some kind of material like this, and it has a large number of sodium or sodium ions or protons at the surface of this molecular structure or the crystal structure. Okay, you have calcium and magnesium in solution. What will happen is that the sodium will go into solution and calcium and magnesium will attach. For every 2 sodiums brought into solution, you will get attachment of 1 calcium or 1 magnesium to the surface. So that is called ion exchange. So this ion exchange is where sodium ions or protons are exchanged for divalent calcium and magnesium. So it's 2 for 1, obviously, because again, the charges have to be maintained. These protons and sodium ions are not going to contribute to hardness. So you get a net, because what is hardness? Hardness is due to calcium and magnesium. It is not associated with any other ion. So you automatically get removal of hardness. Regeneration is required. Now, it's a finite surface area. So this finite surface area needs to be, when it is exhausted, it needs to be regenerated. It can be done, regeneration is generally done by applying sodium chloride salt. So it's very easy to bring the sodium back on the surface of these zeolites. These zeolites can be natural, they can be artificial or synthetic resins. All that is possible. So you get very, very high removal efficiencies. You can get up to 99% or even more removal of these calcium and magnesium ions. So very high removal efficiencies are possible. So that's all about hardness. Let's now take a look at another problem that is common in groundwater, which is not related to hardness, and that is high salinity. Now, high salinity or salinity by itself is measured in terms of TDS. TDS stands for total dissolved solids. Now, total dissolved solids can be, it's very difficult to do it in the proper way. It takes more than 24 hours to measure TDS. Okay, what we normally do is we take a water sample, you have to evaporate the whole thing and then measure the difference. Now, if you're dealing with drinking water samples, then the change in weight of that sample is going to be so small that it sometimes becomes very difficult to measure in the lab. But that's what is required, that you evaporate the water completely and measure the weight of the salt left behind. Okay, so it's a tedious and not easy to do process. Okay, so there is a shortcut, and the shortcut is electrical conductivity. So these days we have portable electrical conductivity probes. They are just the size of your digital thermometers. They even look like your digital thermometers. So you get a readout, just like you have your temperature readout, you get a electrical conductivity readout. And once you know the conversion factor, you do the TDS a few times in the lab, and the remaining time you do it on the site itself. You take your electrical conductivity probe. It's a pocket sized probe. You go anywhere, dip it in water. And those of you who have home treatment systems, if you have a home treatment system, these guys, the ones who run the RO systems and what are the other things that they have, membrane filters and all these things, they will often come and fix the electrical conductivity or TDS, and they use it using and they do it using this electrical conductivity meter. So it's called a conductivity meter, and it's measured in microsiemens or micromoles. Okay, so that's the conductivity, inverse of resistance. The conversion factor is 0.55 to 0.75, and you have to determine it for every water. We generally take the center point. It's an empirical relationship, so you multiply it either by 0.6 or 0.65. Whatever you do, it has to have some rationale to it. So this is the easy way to measure salinity. Now, if I were to ask you, where is the electrical conductivity? What is the difference between TDS and electrical conductivity? TDS includes organic compounds. Electrical conductivity, on the other hand, does not include organic compounds. It includes only ions, because conductivity is due to ions only. It is not due to organic compounds. So there is a small difference between TDS and electrical conductivity. But like I said, in drinking water samples, if they are good quality water to begin with, it's not a major issue. But if it is poor quality water or some other type of water, then you may have a serious problem in using this equation or in this approximation. So we then have to classify waters based on salinity. So salinity is expressed as TDS in milligrams per liter. Fresh water is defined as anything with TDS less than 500 milligrams per liter. And we know that our freshwater examples are rivers, lakes, groundwater. Some of them are all in this range. This is what we want. And I would also like to mention at this point that even plants prefer the same fresh water. So if I want less than 500 milligrams per liter of TDS, the plants will not survive beyond 1,000. So most plants are not capable of dealing with water with more than 1,000 milligrams per liter of, excuse me, of salinity or TDS. So this is a major issue, that for drinking water as well as for irrigation, we need TDS that is below 500 milligrams per liter. So everyone needs the same thing. Then we come to slightly saline. So you have groundwater, river water, lake water, anything from between 500 to 1,000 can be tolerated, but it's kind of difficult. It does cause problems. For human beings, it causes taste problems. And for plants, many of the sensitive plants cannot survive. Then we come to mildly saline. So in the coastal areas where the freshwater stream meets the seawater, that area is called estuarine or estuaries. So these are mildly saline water bodies, and they have TDS from 1000 to 2000 or even higher. Then you have moderately saline. Moderately saline means inland and brackish water, 2000 to 10,000. Severely saline is inland and coastal water, 10,000 to 30,000. Seawater is 30,000 to 36,000 milligrams per liter. How do we deal with this problem? And remember that there are several areas, in fact, very large areas in our country and around the globe have no other problem except that the water in their regions are extremely saline. So demineralization or desalination, another very common word that we use is desalination. So demineralization or desalination of water is one of the most important drinking water treatment processes. So there are many options that are available. Distillation used to be very common, but today the industry is dominated by distillation and reverse osmosis. RO stands for reverse osmosis. So in the water scarce regions of our country, if you can think of Gujarat, Maharashtra, Rajasthan, Andhra Pradesh, Telangana, all these areas, all these states have water scarce areas where the water that is available is, first of all, it's scarce, and whatever is available tends to be brackish. So this kind of brackish water needs to be treated, and the only thing that needs to be done is demineralization or desalination. So we have membrane processes, we have electricity-driven membrane processes. They are called electrodialysis and electrodialysis reversal, and we have reverse osmosis. And I said, I've already mentioned that reverse osmosis is today the most effective and the most popular desalination process. Even distillation, which used to be popular before RO became as popular as it is, reverse osmosis today rules the drinking water desalination part of the industry. Then there is something called freezing and thawing. I'm not going to go into that. I will give you a little bit about reverse osmosis because, like I said, everything else is becoming redundant. Before we go to reverse osmosis, let's go to water membrane processes. So any process in which a membrane is used to push high quality water while rejecting dissolved and suspended solids is called a membrane process. This is a conventional symbol that is used to show a membrane process. So it's a rectangle with a diagonal across it. So the rectangle represents a kind of cylinder. The cylinder can be a cartridge. It's generally another thing for all of you to remember is that especially in RO systems, you generally have a cartridge, and the cartridge has different types of filters. So you may have these noodle type filters. So these noodles, if you can imagine your noodle, and you can imagine your noodle as a hollow fiber. So the entire cartridge is filled with hundreds of these noodle-like hollow fibers. And the water is pushing, it's coming in under pressure. It's pushing against the fiber material, and only high quality water is pushed through the pores of this membrane, and whatever is rejected is called the concentrate or rejectate. So this is our raw water, this is our treated water, and it's as simple as that. Okay. So that is, in a very, very simplistic way, that is a membrane process. What are the applications of membrane processes? I've already said to you that desalination, removal of salts, that is the biggest one. The second one, and I think I mentioned while I was talking about disinfection, one of the problems with disinfection is that when you add chlorine to water, it reacts with NOM. NOM is natural organic water and natural organic matter, And when natural organic matter reacts with chlorine, it will form disinfection byproducts. So we want to avoid that. NOM again is non-toxic, but because it creates other problems down the road, therefore we want to remove it. So again, it's the same issue that these are non-toxic materials, but because they cause other problems, they need to be removed. So major applications are removal of NOM as well as salts. We also use this principle in analytical instruments and methods. So many of the analytical instruments and methods that we use have either pre-filters or not just membranes can be made out of pre-filters, but the kind of membranes that we are looking at here, they are all high-end membrane processes. So they are used to get very high quality water. There are several industrial applications. In medical applications, membrane processes are used for the separation of different components of body fluids, and you can have purification processes in the manufacture of any number of products. Now, let's take again, like I said, a very simple view of the membrane process, and you can use it to do simple calculations. So, if we do a mass balance around water, Q0 is the flow rate of water coming in. It is divided. There are two outputs. QP is the permeate. P stands for permeate. R stands for rejectate. So QP is the quantity of permeate, the flow rate of the permeate, and QR is the flow rate of the rejectate. And so if you do a mass balance around water, Q0 is equal to QP plus QR. I want to do a mass balance for the salts. I want to remove the salts. I want to look at the efficiency of the membrane in removing the salts. So the total amount of salts, C0 is the TDS in the raw water. So Q0 C0 is the input. What is the output? QP CP plus QR CR. Let me see. I don't have any practice problems here. I will upload them separately so that you can do some practice problems on your own. And I've kept it as simple as possible because we don't have enough time for doing more than this. And I'll be uploading it today itself. Okay, so we'll stop with water treatment here and we will start with wastewater treatment in 2 minutes. So let's take a 1-minute break and then we'll start again. How many students have joined?
No one. It's just three
No
of
one
us.
is there.
It's just the three of us.
Yes, ma'am.
Yes.
Okay, that's easy. You guys have to make an assignment.
Okay.
Okay. Yeah. So I'll share some material with you, and I will be uploading the slides as well.
Okay, ma'am.
Okay, so let's get started with the second part of this topic, and that is wastewater treatment. Now, when I started talking about water treatment, I showed you a schematic that was basically that you have a well or surface water intake. From there, the water goes to a water treatment plant, and from the water treatment plant, it goes to a distribution network. Now, this distribution network is where the consumer gets the water. So the water at my tap, I am the consumer, and when I open a tap, that is the end point of the distribution network. Now, when I utilize water, whether I'm using it for cleaning, for drinking, for cooking, for gardening, whatever it is that I'm using the water for, a large portion of the water that I use will end up in the sewer system. So it's going down the drain. Some of it is consumptive use, like gardening, drinking, cooking, those are consumptive uses. But then you have wastewater that goes to the toilets and that goes in other parts of the areas that you're using water. Some of it will enter into the drainage system. And from the drainage system, it goes to the wastewater treatment plant. And that is what we're going to look at in the remaining part of this topic. Now, after it goes to the treatment plant, why do we first of all have to treat water? In water pollution, I already said to you that wastewater, if it is discharged into the river or on land and so on, it will contaminate the surface water body, it will contaminate the groundwater, and that will lead to problems in terms of the quality of the water, and it will cause harm to the ecosystems. So, for all these reasons, we have to treat wastewater. Now, after treating it, you can discharge it to land, surface water, or to the sea. But today, when people are becoming very conscious of the fact that water needs to be conserved, that after all, we are putting in so much effort, so much expenditure in treating the water, then it should be reused. So, if it is adequately treated, then it can be reused. And the most common reuse application is irrigation. So I will be covering this part in this topic. So the boxes that are shown in yellow are the ones that we're going to cover in this part of the topic. So let's start with a schematic of conventional municipal wastewater treatment. Now, when I say conventional, it includes two levels. It includes primary and secondary level of treatment. And tertiary and higher levels of treatment are considered advanced wastewater treatment. Okay, so we are going to restrict ourselves to conventional municipal wastewater treatment. So this sewage, when it enters the wastewater treatment plant, it goes through screens. And I'll show you an example of those screens. These are screens. They can be vertical or they can be inclined. And you can see that they stop all kinds of large, what we call large objectionable solids are removed. So the water that is coming into the the wastewater treatment plant is passing through these parallel bars. And like I said, they can be either vertical or inclined. And in this case, they are static bars and they have to be cleaned manually. But in some wastewater treatment plants and more modern plants, you have mechanical screens. So they are automatically cleaned. The way they are designed, they get cleaned mechanically. So I don't have photos over here. I haven't included it, but they do exist. Okay. So here the water is flowing through these parallel bars. Okay, and that is so that all large materials, so you have plastics, you have twigs and branches and leaves and paper and all kinds of rubbish comes into the plant, and that has to be prevented from entering the plant. So this is the first point. So that is the first thing. Okay. Now what else is passing through those bars? The second thing that passes through those bars is gravel and pebbles and sand and so on. Now these are discrete particles. You have already seen the definition of discrete particles. So primary sedimentation can be used, grit chamber or primary sedimentation can be used for the removal of these discrete particles. So that is our primary level of treatment. Now, this wastewater has a huge amount of organic matter. Where is this organic matter coming from? It's basically fecal matter and other body fluids, basically waste excreta, mainly from human beings, but it can also include animal waste as well. Okay, so all this is very high in BOD. So the BOD levels of wastewater after this discrete particles have been removed is very high. So that is taken for aerobic treatment. I don't know if I have impressed upon you enough by now that when you have organic matter and you add oxygen to it, it will eventually get converted to CO2 and water. Now, if it's a biological process, this material, this reaction is biologically mediated, which means one of the other end products is biomass. So in aerobic treatment processes, we'll cover about 3 of them. We'll go through activated sludge process, trickling filters, and rotating biological contactors. So these are the 3 aerobic treatment processes that I have included in this PPT, but you will find many others in the books and so on. So there are several examples, and I'll go through quite a few of them. So you'll be able to understand what aerobic biological treatment is. Now, because one of the end products is biomass, therefore, you need a method for removing that biomass, because that biomass is still organic matter and it's highly biodegradable organic matter. So that is what we call sludge. So we take the material from the aeration tank. From the aeration tank, it goes to what we call a secondary clarifier. And from the secondary, now what happens in the secondary clarifier is that the biomass that is generated is going to settle. And that settled biomass is called sludge. And that sludge can be taken further for anaerobic digestion. Now, this anaerobic digestion is done in the absence of oxygen, and in that process, we also get generation of biogas. Now, because in big cities, the amount of municipal wastewater that is being generated is huge, it is economical for the municipal authorities to set up anaerobic digesters and generate biogas, because this is a good fuel. It's a good quality pure fuel which can be utilized. So you get sludge from 2 settling processes. The primary sedimentation tank may have a significant amount of organic material, and the secondary clarifier is completely organic biomass that comes into the anaerobic digester. The clarified liquid or effluent from the secondary clarifier can then be discharged or sent for reuse. So there was a time when secondary wastewater treatment was considered sufficient for irrigation and so on, and perhaps under certain conditions it's still sufficient, but many more and more people feel that there is another level of treatment that is required prior to reuse. It all depends on the applications. So that is how the water goes. Now, this sludge which goes to the anaerobic digester, the volume and the weight of the sludge is going to be reduced tremendously because of the anaerobic digestion process. So one thing is that biogas will be generated. Second thing is the amount of sludge will be reduced in volume. And finally, the water from that biomass will be removed by various processes. I'll give you some examples. That is called dewatering of the sludge. That liquid can again be discharged along with the other materials, and the remaining solids, which are somewhat dry, not entirely dry, but somewhat dry, they can then be taken for landfilling or incineration. That's a very simplistic, in a nutshell, view of municipal wastewater treatment. So what are our main parameters? Our main parameters, first of all, are BOD and COD. So like I said, in general, for untreated sewage, the BOD5 value is anywhere from 100 to 300 milligrams per liter, and COD is 250 to 1000 milligrams per liter. Then we have solids. Total solids are TSS plus TDS. Suspended solids can be anywhere from 100 to 350 milligrams per liter. Total dissolved solids can be 200 to 1000 milligrams per liter. And then we have nitrogen. Remember what I said about the important nutrients. So we have nitrogen and phosphorus, which are the most important nutrients. TKN stands for total gel-dull nitrogen. So that includes, I've written all nitrogen species, but it includes organic ammonia and organic nitrogen and ammonia, not nitrate and nitrite. So that is 20 to 80 milligrams per liter, and total phosphorus is 5 to 20 milligrams per liter. So the list of standards for, there are two things that I want to impress upon you in this particular slide. The first thing that I want you to remember is that the standards include standards for several different parameters, and all of them do not apply to all wastewaters. What I'm showing you here in this slide is just an illustrative example of the main wastewater standards for discharge. And these are the basic ones, the ones that I've already explained in previous lectures, so you'll be able to understand them. But the actual standards are much bigger. There are many, many more parameters. So please make sure, if you ever have to do this, please make sure that you go through the entire list of standards. And the second thing that I want to impress upon you is the four options for discharge. The wastewater can be discharged into an inland surface water body. So I may have a river, a stream, anything, lake, pond, people are discharging wastewater into them. But they have to meet these standards. So this is the first column for discharge. So these are the standards that they have to make sure that they meet. Then we come to public sewers. So in a campus like ours, our wastewater is going directly to the public sewer. And from there, it goes to the wastewater treatment plant. So you can see that the standards are far more relaxed compared to all the others, because it's actually going to a wastewater treatment plant. Can you use wastewater without treatment? If you're going to use it for irrigation, then it has to meet this column of standards. Okay, so this is the third column that you need to make sure that all the wastewater meets these standards. And I'm not going to read out all of that. It's for you to spend some time and read it. I will be uploading the slides, so you'll be able to do that. And finally, you have marine and coastal areas. So marine and coastal areas, the standards are again quite relaxed compared to inland surface water bodies. And you can see the standards for marine and coastal environments. Now we come to the primary settling processes, the primary processes or the primary treatment processes. So when we talk about primary treatment, the objective of primary treatment is removal of objectionable solids. I've already shown you examples of removal of these large solids. So the first step is screening. Then in screening, we have parallel bars with spacing of 2 to 7 centimeters. You can use wire mesh. Now, I've shown you photos of parallel bars, but you can also have parallel and horizontal bars. So that will create a wire mesh and that will give you smaller openings. So it provides a barrier. So you get a loss of head. There's some head loss over there. But by and large, it will give you better results because many of the solids which do enter the wastewater treatment plant will be kept out more effectively. Some wastewater treatment plants use what are called comminutors. Comminutors are grinders. Just a technical name for grinders is comminution. So comminution is where you grind the organic matter. So if you have twigs and leaves and branches, they can all get ground up very to small amounts. So this ground material, contributes to BOD and COD of the wastewater. Comminutors for grinding of coarse materials can be used, like I said, and it will contribute to the BOD and COD of the water. Remember, BOD and COD are associated with organic matter. Then we come to grit chamber. I already said if you have sand and gravel and pebbles and stuff like that in your wastewater, then you provide a long channel, and this long channel will allow the discrete particles like sand and grit to settle. So these are heavy, they will settle on their own, and only few minute detention time is required. Then we come to primary settling. Primary settling has a detention time of 2 to 3 hours. You can get removal of 50 to 65% of the suspended solids and 25 to 40% of the BOD in primary settling. Primary settling is also based on discrete settling. It is not like flocculation, it is more like simple discrete settling. So finer particles like silt and sand will be removed in primary settling. And you will get removal of organic matter that is associated with these particles. That will happen as well. It happens naturally. It's yes. So these tanks can either be round or rectangular, and the sludge has to be removed further. We will look at that later. And the key design parameters are the detention time and the overflow rate. So I'll give you some practice problems. You'll be able to understand how to, they're very simple. It's very, very simple to do it. Then we come to secondary treatment. Secondary treatment means you want to remove the BOD. BOD is associated with organic matter. I've already spent a long time on BOD and the relationship with organic matter. So by now, you know exactly what removal of BOD is and what the importance is. So the most common, most popular process is activated sludge process. And the activated sludge process has two parts. One is aeration tank and the second is the secondary settling tank. Now the secondary settling tank is also called the secondary clarifier. So clarifier means, clarification means that you are allowing the material that is in suspension to be removed by settling. And I also should mention at this point that biomass, which is difficult to remove, I've already said that bacteria are biological particles, they are colloidal in nature and so on. But when the concentration of biomass increases the way it does in activated sludge process, bacteria are sticky colloidal particles. They stick together, they form large flock, and this large flock is easy to settle in a secondary clarifier. There are several options. Other than activated sludge process, we have trickling filters, we have rotating biological contactors, and we have oxidation points. So that is what we do in the secondary removal of BOD. Now, this sludge that is coming out of these processes, all of these processes are generating sludge. This sludge has to be managed. And I can tell you that I think there is some, I don't know if I still have it. No, I have removed it, but sludge management is a very, very big part of wastewater treatment. I think 50% of their cost and 30 or maybe 30% of their cost and 50% of their problems are associated with sludge management. So this is a huge problem for municipal wastewater treatment. So the first thing is thickening. Thickening means you want to take out as much of the water as possible and make the sludge less in quantity, because it's a huge part of the output from the wastewater treatment plant. Then the second part is anaerobic digestion. So if you use anaerobic digesters, you have the benefit of you are reducing the amount of sludge generated in a big way, because one, you're removing water, two, the sludge itself, the biomass, the organic matter is being converted not to CO2 and water. We are dealing with fermentation conditions or anaerobic conditions, and in those conditions you will get what is called CO2 and methane. So we will come to that. So there is an enormous reduction in the amount of sludge generated, and you also have the added benefit of generating biogas, which is a useful fuel. So that is the second one. Then the third one is dewatering. So if I can remove almost all the water, it's not possible to remove all the water, but almost all is good enough. And so that is called sludge dewatering. So you want it to be as dry as possible. Depending on the quality of the sludge, it can be used as compost or manure. And if it is contaminated, which it often is in urban areas, then it cannot be used for anything. So you can either incinerate it or take it to a landfill. So that is the last part, and that is disposal. I have added tertiary treatment as well. Not sometimes, very often, the effluent coming out of conventional wastewater treatment plants is rich in nutrients like nitrogen and phosphorus. So even good and efficient municipal wastewater treatment plants, even though they have met the secondary objectives, or rather their secondary part of the treatment plant is working well, it's meeting all the standards, even then the water body may not be healthy because it's getting eutrophied. So eutrophication happens when the level of nutrients is high, nitrogen and phosphorus levels are high. So it becomes necessary to have tertiary treatment and to prevent eutrophication of these water bodies. So nowadays the standards have been tightened to some extent, and we do have to so we do have to prevent eutrophication of these water bodies, and therefore tertiary treatment is perhaps becoming necessary in many of the urban centers. And you can use a mix of biological and or chemical processes for achieving these objectives. I've already shown you this. So now let's go to wastewater treatment. Okay, so let's take the first one, which is ASP, activated sludge process. Now, why do we call it activated sludge process? Activated means it's active, it's alive, and the sludge is the biomass. Biomass in this case is bacteria, and they are aerobic heterotrophic bacteria for the most part. So it's called activated sludge process. So here we have suspended growth, and this suspended growth process is run as a mixed flow reactor. So we also call it CSTR. If you're from chemical engineering, you know what a CSTR is. A CSTR is a tank where everything within the tank is completely mixed. So we say it's 100% mixing, and it's a constantly stirred or continuously stirred tank reactor. So it's suspended growth. Suspended growth is for the biomass, for the bacteria, and we have mixed flow reactor for BOD removal. Now, what does the bacteria need for consuming the organic matter? All it needs is oxygen. So the first thing is the aeration tank. The aeration tank has to be provided to maximize DO levels in the wastewater for biological growth to happen. The detention time can be anywhere from 6 to 8 hours. Okay. As I said, what is the end product of this reaction? The end product of, let's say, organic matter plus oxygen is going to be CO2 plus water plus biomass. Okay. Now, that is our sum total in terms of a reaction. Now, this reaction, which is going to result in so much biomass, that biomass has to be removed. So we then go for a second unit, which is the settling tank or the clarifier for the biological particles that need to settle. This biomass can be recycled, because if we maintain a certain level of biomass within the aeration tank, it has to be an optimum level so that there is enough biomass to be able to take up all that new organic matter that is coming in with the fresh effluent from the fresh wastewater. Okay, so that is the recycling of solids from the clarifier to the aeration tank to ensure a constant bacterial population. So that is to maintain steady state conditions and a constant bacterial population. So a significant chunk of the total biomass is recycled and the remaining is wasted and sent to the sludge management units. So sludge handling and disposal is the final part. This is the most popular process for domestic wastewater treatment. The advantages, why is it so popular? The first thing is dilution. Now, remember that the seasons change, and when the seasons change, the amount of wastewater coming in is going to vary. So if you look at the annual variation in wastewater loading in terms of volumetric flow, there is a huge amount of flow fluctuation. So the flow will fluctuate throughout the year, from summer to monsoon to winter. Now in monsoon, what happens is, because of storm water, if the urban center has a mixture of stormwater and wastewater, then the flow coming into the plant is going to be enormous. So the flow fluctuation can be huge. And that means that you get enormous dilution, but you can also get what is called washout. So these are some of the things that this process is good at handling. So all these fluctuations, that is one example. Then we come to toxic shock loads and so on. Let's imagine that some small scale or medium scale industry within the city is dumping a shock load of some toxic material. It goes down the drain. Now, if you have any other type of process, it's a toxic shock load which will destroy the biomass, because the bacteria are biological particles and they are as susceptible to toxicity as any other organism. But because of dilution, this toxic shock load will be taken care of. So they can withstand a significant toxic shock load, which other processes cannot withstand. So for this reason, this is the main reason for utilizing activated sludge processes. The disadvantages are that it requires a very large amount of land. And the second point is that aeration, the aeration part of the process, requires a huge energy input. So many municipalities, even in our country, they get grants for setting up the plant, but they don't run it because it's so expensive in terms of energy, because many cities don't have enough power and they are not able to run these plants. So you will find that very few wastewater treatment plants are actually running at full capacity and doing what they are designed to do. Okay, then we come to a few more details. So this is, like I said, the two-step process. You have the aeration tank, air or oxygen. You can have pure oxygen or you can have air. It goes inside the tank through what are called diffusers, or yeah, they can be coarse diffusers or fine diffusers. They bubble into the tank and they are simply there to provide oxygen for the biomass to grow. So this water then goes to a settling tank, and because there is a huge amount of biomass that has been generated, the biological particles or bacteria will stick together, they will form floc, and they will settle to the bottom over here. At the top, you will have clear liquid, and that is our objective. So this clear liquid will then be taken for either tertiary treatment or for disposal. Then the sludge, the biomass that is generated, part of it will go back because we cannot allow the tank to become clean. We need the biomass to keep the process going. So a fraction will come back to the aeration tank and the excess will be sent for sludge management and disposal. Okay, so these are the end products. The end products are carbon dioxide, water, and biomass. It's a fully aerobic process where organic matter is being converted to CO2, water, and biomass. So this is surface aeration. This is what is called a turbine aerator. So a turbine aerator is nothing else but just a turbine type aerator, which is suspended in this case from an overbridge. And you can see all it's doing is causing turbulence in the water. And this huge amount of turbulence means there is a huge interfacial surface area for the oxygen to come into the water. That's all there is. So atmospheric oxygen comes into the water simply because of the turbulence that is generated. This is another example of a turbine aerator. It has been tethered to the tank at four ends, and you can see how much turbulence it's creating, and that is the way to generate, to bring in oxygen into the tank. These are the same turbine aerators when they are not operating. So you can see the large number of aerators in the tank when they are not operating. These are again turbine aerators. They are tethered to four corners of the tank, and you can see the only part of the whole thing is the fact that they're causing lots of turbulence to increase the atmospheric oxygen level inside the water. This is diffused aeration, and what you cannot see here is there is a main pipe in which the air or oxygen is coming in. The nozzles are pointing inwards or downwards, and you can see the froth. The froth on the surface of this tank is an indication that the oxygen is coming in from the top here, not from the bottom. And these are nozzles, the downward pointing nozzles. There are several other methods. You can have upward pointing nozzles or diffusers. You can have all kinds of aeration tanks, and people have tried everything, and there's always some amount of success with all of these. Then we come to trickling filters. Now, I mentioned in activated sludge process, the biomass is suspended. Here, the biomass is attached to the surface of media, and the media can be rock, stones, or plastic media. This is plastic media. It's corrugated plastic, and you can see these corrugated sheets. They can be put together in different ways. So you have these corrugated sheets where you have a lot of porous space, and the water, you can see how the water is being distributed. So this is what are called the sprinkler arms, and the sprinkler arms have nozzles pointing in opposite directions. So as the sprinkler is rotating, you get this distribution of water over the entire surface area of the trickling filter. So this is on the right is an old trickling filter, and on the left is a biofilter. And these biofilters are very tall compared to the old rock and stone type filters. So these are plastic media. These are all plastic media. You can see the output in terms of wastewater. So this wastewater that is coming at the top is huge in amount compared to the rock and salt, stone, not rock and stone type filters. So the bed media can be ordinary rocks or plastic. Let me also finish one more thing. So it's called attached growth because the biomass or the bacteria are growing attached to the bed media. So the bed itself is the filter bed. It's a static mass, and the mass is rocks, plastic, whatever it is, stones. These are the kinds of materials that are used in the filter bed. And because the biomass is growing attached to that filter bed, it's called attached growth. If there is very little recycling, it's a plug flow reactor. A plug flow reactor is defined as one which has zero mixing in the direction of flow. So if there is no recycle, it resembles a plug flow reactor. If you have a high rate of recycle, then it starts resembling a constantly stirred tank reactor. Okay. Now the bed diameter can be as large as 60 meters, or it can be very tall in what are called biotowers. So bed depth with rocks is restricted to 3 meters. With plastic, it can be much higher. It can go as high as 30 meters. Okay, so these plastic biotowers, plastic media biotowers have been quite successful in many places, and their footprint, the biggest advantage of these biotowers is that their footprint is much smaller and you get higher efficiency compared to the rock-based media. There are several problems in terms of managing trickling filters which are based on rocks and stones. You can use distributor arms to sprinkle the wastewater evenly, uniformly at the top. The void spaces in these types of media, whether it's rock or stone or plastic, is very large. So there are huge air spaces, and that is essential for ensuring that water flows freely. I'm sorry, not just water, but air and water will circulate freely through the media, and that is essential for the efficiency of the process. Biological growth will happen. You will get growth of bacteria, algae, fungi, protozoa, worms, insects, larvae, all kinds of things will. It'll be an ecosystem in itself in many cases. Then we come to recycling. So like I said, recycling of the effluent will make it more efficient, and it will prevent the slime layer. So remember, it's attached growth. So attached growth means it creates a biofilm, and this biofilm is what we call a slime layer. So this slime layer will not dry out if you recycle the effluent. Obviously not the entire material, only a fraction of the entire material will have to be recycled, and that is essential for making sure that the entire attached growth does not dry out. What is the advantage of this process? Why should I use it? The first thing is that because it's a plug flow reactor, the removal efficiency is much higher. So it's again lack of time to help you understand that plug flow reactors are always more efficient than CSTRs, and that is the biggest advantage. The second thing is, because it's more efficient and it's a plug flow reactor, the footprint, the land area requirement is much less. What are the problems? There are several problems that make it unpopular. The first thing you should know is that when a process is more efficient, it's also more sensitive to fluctuations. So if you design it for a particular flow rate and a particular organic loading, any fluctuation in the flow rate or the organic loading means there will be problems in the output. So it is extremely sensitive. So the first point is removal efficiency is higher, but it's also extremely sensitive to fluctuations in quantity and quality. There is no dilution. So that dilution, which helps in buffering these fluctuations, is not there over here. So it cannot withstand toxic or shock loading. That is the biggest problem. The next major issue is washing out in monsoon and drying out in summer. Now, let's say there is water scarcity in summer. There's no water. So you will let the no water comes into the trickling filter. What will happen? The entire biomass will die. And once the biomass is dead, it will take at least another month to bring it back when the water comes back. So this is a huge problem. And in monsoon, if it is open to the atmosphere, if there is no cover on these trickling filters, what will happen? The biomass will get washed out. Because in our country, when it rains hard. And it's sufficient intensity to wash the biomass out. Then we come to the next process. The next process is the rotating biological contactor. This is again an attached growth process, but it's not a plug flow reactor. Let me show you a schematic. This is again from Wikipedia. Yeah. And you have a side view and a front view. These tanks are huge. They are tens of meters in length and a few meters in diameter. And I've seen some photos on the internet. You can see them for yourself. They're probably about, I would say, about 15 to 20 feet in diameter, each disc. So the height would be about 20 to 30 feet, perhaps. Yeah, 10 meters, yes, easily. And okay, so this is, like I said, a side view, and this is a front view. The water comes into a large tank. There is a shaft at the top of the tank on which rotating plastic discs are mounted, and there is a very small spacing between each of these rotating discs. Now, these media discs, they are always made of plastic because this is the disc that is going to support the growth of the biomass. And this biomass and the disc has to be as light as possible, and the whole thing is rotating at all times. The water is in the tank, so this entire biomass is alternately going first into the water, then into the air, back into the water, back into the air. So this is something that's happening. It's not really a wet and dry cycle because the rotational speed is pretty high. And you get a series. That's what this is all about. So the diameter is 3.6 in this case, but you can have very big ones. Yeah. So the slime builds up on the disc surface. These are, again, these are, I would say, not irregularly shaped, but the disc is not smooth. Let's put it this way. What's the word I'm looking for? So the disc surface is very rough, and that allows the slime to build up on the disc surface. And only 40% of the disc area is submerged in the wastewater, and the biomass is growing on both sides of the disc. Okay, so that's one thing. Let me see what else I can say to you. What people found out, I have mentioned this in my PG level class, that the problem with this method is that the weight, as the biomass increases on the disc, the weight on the discs is becoming heavier and heavier, so the shaft has to take that increased weight. And very often there has been failure of these RBCs because of the excessive weight on the shaft. So the shaft literally breaks into two because of the excessive weight of biomass. The advantage of this process is that it's a CSTR, so it has the ability to withstand shock loading, but at the same time, because of this shaft, I think if they were to run it as a smaller smaller tanks and more frequent cleaning of the discs, it might be a better idea. I don't really know, but I frankly like the idea of plastic biotowers. It makes more sense, and if they're covered, there is no issue of washing out and drying out and all that. So as long as you make the reactors as closed reactors, then it's fine. But operation and maintenance can be a problem because the stench in these closed reactors can be unbearable. So again, from an operational and maintenance point of view, that's a major issue. Then we come to sludge treatment and disposal. So like I said, this is a huge part of wastewater treatment. It is sludge is about 2% of the total volume of the wastewater ends up as sludge. It has about 1 to 5% solids. So when I say what is the moisture content of sludge, it can be from 95% to 99% is water. So sludge management is a major issue. 40 to 60% of the construction cost, 50% of the operation cost, and all of the problems are generally associated with sludge management. Let's look at anaerobic digestion. So the sludge that comes out of the activated sludge process is then taken for anaerobic digestion. The first and primary objective of anaerobic digestion is to reduce the sludge volume. Okay, the objective is to reduce the sludge volume. Anaerobic digestion by nature is much slower than aerobic digestion. Because of that, the detention time is in the order of days, not hours. So the mean cell retention time is anywhere from 10 to 15 days. The biomass has to be kept inside the digester for at least 10 to 15 days. The the hydraulic detention time is much less. I can mention that as well. Give me a minute. Um, I don't think I've mentioned it, but the HRT can be much less than the mean cell detention time, but the mean cell detention time is about 10 to 15 days. Then I've already mentioned the fact that biogas is one of the most useful end products, carbon dioxide and methane, and it's a complex three-step process. So let's take a look at that. So what happens in anaerobic biodegradation? It's not as simple as aerobic biodegradation. So here we have our sludge. The sludge is biomass. This biomass is basically bacteria and a few other types of microorganisms. These are complex polymers. So they are polysaccharides, lipids, proteins, all these kinds of biomolecules, biopolymers are part of sludge. The first thing that has to be done, because remember that anaerobic bacteria are going to utilize this organic matter and convert it to CO2 and methane. So the first thing that has to be done is that the complex polymers have to be broken down into their monomeric unit, which can then be digested further by the microorganisms. So the first thing that is there in this process is hydrolysis by extracellular microbial enzymes. So these microorganisms are going to excrete extracellular enzymes out of their cell, which will mediate the hydrolysis of these complex polymers. And then once it's broken down into sugars, fatty acids, amino acids, and so on, then these bacteria will then be able to take up these monomeric units and convert them to acids. So I've shown you only one acid over here, acetate or acetic acid. You can have any number of acids. You can have propionic acid, butyric acid, and so on. So all kinds of acids will be generated. They are called volatile fatty acids. And acetate is one of the most important fatty acids that are generated in this process, in this acetogenesis process. So in many cases, it deserves a separate name for itself because the group of bacteria that are involved in generation of acetate are called acetogens. So there are all kinds of bacteria. It's a microbial consortium that is responsible for this entire process. It is not done by one type of bacteria. There are several types of bacteria, several groups of bacteria that are involved in anaerobic digestion. So acetogenesis results in acetate, and another product that is part of this process is hydrogen gas along with carbon dioxide. Now, this hydrogen gas along with carbon dioxide and this acetate will be utilized by another group of bacteria called methanogens. These methanogens are strictly anaerobic bacteria, which means they cannot tolerate the presence of oxygen. They grow only in the absence of oxygen, and they will convert these compounds to methane and CO2. So this is our biogas. Methane plus CO2 together is called that process is called methanogenesis, and the bacteria that are involved in this process are called methanogenic bacteria. Um, so about 20 to 30 years ago, most municipalities used to go for what were called conventional digesters. The conventional digesters had two types of covers. They had fixed or floating covers. So the wastewater sludge would come into the digester, and as the gas is forming, the entire cover would lift to provide equal or constant pressure. So those were called floating anaerobic digesters. They were quite popular in the country at that time. About, I would say, 30 years ago, I've seen a lot of them. And some of them are fixed covers, and the fixed cover means that the pressure builds up over time. Now, one of the problems with these digesters were that they required a fair amount of time. In some cases, they required heating depending on the ambient temperature levels in that area, and they sometimes required mixing, and operational and maintenance issues were a major problem because cleaning these tanks periodically was a major issue. So people have now started making what are called egg-shaped digesters. Now these egg-shaped digesters have this kind of profile or cross-section, and the advantage of having an egg-shaped digester is that the gas is accumulating more easily at the top. You don't have to have fixed or floating covers. There are less operational and maintenance problems. I have read a claim where people are saying they don't need to be cleaned at all. So you can run them for years and years and no cleaning is required. So that's a huge advantage that is claimed for these egg-shaped digesters. I haven't seen any in India yet. Maybe they'll come up with something soon. Now, this is the internal part of the egg-shaped digester. It's a concrete tank. You can see that the footprint is much lower. So the land area requirement is much lower. And they also claim that they don't require mixing and heating. And the external cladding, you can see the scale. This is the human being standing in front of the digester. So in terms of the scale, you can see how large these digesters are. And no mixing, no heating is required because it retains the heat that is generated during the process. So these are photos of anaerobic egg-shaped digesters. And they are made out of reinforced concrete with external cladding, and the external cladding is to retain the heat as well as absorb solar heat. Then we come to the last part, and the last part is disposal. How do we dispose of the sludge that is remaining even after anaerobic digestion? So for that, there are several things that are necessary. The first thing that is necessary is to remove the water from the sludge. So dewatering and drying of the remaining sludge solids is the first thing. There are several ways it can be done. You can use drying beds. So you allow the wastewater that is there. It will have a high amount of solids. These drying beds can be layered with sand or gravel at the bottom, and the sludge comes in at the top, and the water is allowed to evaporate. So they are called drying beds. That is one thing. The second one is vacuum filters. The vacuum filters are literally vacuum filters. You apply a suction pressure and the water is removed with the solids remaining on the filter. So that is a very common method, but remember that applying vacuum filtration is an expensive process. A filter press is exactly what it means, that you press the solids between two filters and the water is removed simply by the pressure. So that is another way of removing the water. And then we come to centrifugation. Centrifugation means you send the sludge into a centrifuge. The solids will be separated from the water is taken for discharge, and the solids are taken to a landfill. And finally, those solids can be taken to an incinerator. So if they are pure organic material, they can be burnt in an incinerator. You can get heat and electricity from that heat. So that is another option. And all these options have been tried, some successfully and others not so successfully. So either way, they're all working. Technically, frankly, I would say at this point, all these options are technically feasible. The problems are in operation management and financial issues. So these are some of the major issues in wastewater treatment. They're all technically successful processes. Whatever is remaining at the end of the day, whether it's ash from the incinerator or solids from any of these processes, will end up in a landfill. I want to say at this point that we are moving towards a time where nobody wants to utilize land for landfilling, because land is becoming more and more difficult to find. Population is increasing, so we want to minimize landfilling. And this is definitely an area that needs to, basically, we want to minimize the amount of solids that go to a landfill. Okay, that is the end of anaerobic digestion, and we have a couple more methods to cover. So then we come to oxidation ponds. Wastewater treatment, you can also use what are called oxidation ponds. Let me show you a photo before I talk about it. This is an oxidation ditch where the water is coming in at one end, and by creating these baffle-like structures, the water is routed through these structures, and that allows a fair amount of mixing, and that is all that is provided in these oxidation ditches. So it's kind of like the aeration tank in an activated sludge process. The only difference is that the detention time is very high and the depth of the pond is not much. It's a shallow pond. So these are very large shallow ponds of 1 to 2 meter depth. Detention time is very high. There is no separation in terms of hydraulic and biomass retention time, which is the case in all the other processes where the biomass is retained for a longer period of time compared to the water. So here there is no split between the two, and it's a single tank process. What else did I want to say? It's a complete mixed process to some extent. It requires, because of the fact that it has a large or a very high hydraulic retention time, because of that, the land area requirement is also very height. So you can't use it in urban areas, but it can be used in suburban and rural areas. So raw water or partially treated sewage is treated further. It's a single step process that can be used when land is freely available. The design concept is same as eutrophication. So what happens in eutrophication is that the nutrients that are coming in with wastewater are being utilized by algae and bacteria. And as the dead algae and dead bacteria start sinking, the bacteria will take over. They will consume this biomass, and that will result in some amount of biomass. Bacterial biomass will be there, but it will also consume the organic matter. So that will be sent into the atmosphere. I should add another graphic over here. I'll do that. So there are three different types of oxidation ponds. One is facultative. If the pond is aerobic at the surface and anaerobic at the bottom. So facultative means you have bacteria which can switch between aerobic as well as anaerobic conditions. And because of that, the pond is called facultative oxidation pond. Aerated lagoons are very common, especially I think in our country. They have become very common in the last few decades. Let me show you that. So this is an aerated lagoon, and it's deeper than your normal oxidation ditch. These are mechanical aerators. Again, they are doing nothing but causing turbulence and bringing more and more water into contact with air. So what that does is that it brings more DO into the water. The problem with bringing DO into the water is oxygen is sparingly soluble in water. So this kind of aeration is necessary to increase the amount of oxygen as far as possible in water. So these are mechanical aerators that are used to ensure that the DO is distributed throughout the volume of the tank. I've already mentioned that you want to remove nitrogen and phosphorus after successfully treating the wastewater to the secondary treatment level. If that is the case, then we have what are called polishing ponds. So in those polishing ponds, you can design them as oxidation ponds. And that is the polishing pond concept. And very often you will find that people grow or cultivate different types of fish, partly to prove that the effluent is no longer toxic, and secondarily to prove that there is that it's sufficiently clean, the water is sufficiently clean and non-toxic. And the one place that I saw a polishing pond, the water was fairly clear, and it becomes obvious that yes, it helps to increase the water quality level tremendously. Then we come to nutrient removal. So like I said, up to this point, I've been talking about secondary treatment, and oxidation ditches are oxidation ponds or ditches are examples of a one-step treatment process. Okay. Now, as I said, if you discharge even well-treated wastewater, which has been treated to the secondary level, if you discharge it into any surface water body, it will cause eutrophication because nitrogen and phosphorus have not been removed. Only a small amount has been removed. And you can see about 30% removal of nitrogen and only 30% removal of phosphate is obtained in conventional wastewater treatment. Now, this remaining nitrogen and phosphorus will encourage algal as well as bacterial growth. It will lead to degradation of the wastewater. Yeah, I'm sorry. It will lead to degradation of the water quality in the receiving water bodies. Okay, so this treatment, tertiary treatment, is required for nitrogen and phosphorus. It can be done either biologically or using physicochemical processes. If you're trying to do if you're trying to remove nitrogen, the best way is nitrification, denitrification. I've talked about nitrification. Nitrification means ammonia going to nitrite and nitrate. And denitrification means that the nitrate is then, along with an organic source, converted to nitrogen gas. So in a sense, the nitrogen cycle is complete. That nitrogen gas, which is bringing nitrogen into bioavailable forms. The bioavailable forms of nitrogen are ammonia, nitrite, and nitrate. These are considered the biologically available forms of nitrogen. Nitrogen gas is inert. It's not going to react either biologically or chemically. So this combination of nitrification, denitrification is the easiest biological process. Detention time required is 15 days. But I would like to add one point over here, which is not often highlighted in many of the textbooks. Bioavailable nitrogen is a fertilizer. When we fertilize our gardens, our fields, and everything else where you have production of plants, in agricultural productivity, bioavailable nitrogen is what you need. That's what people are spending all their money on. And that is essential for growing any plants. So, using this process and sending very useful bioavailable nitrogen back into the atmosphere is a dead loss, because you're literally losing nitrogen. So it's very important to utilize it after nitrification or after in other forms to avoid other problems. There may be some other problems, but secondarily, a secondary treated wastewater is the most popular way of using it is for irrigation. And if there are pathogens in the water, if there are other issues of toxic contaminants and so on, which is very common, then that needs treatment and the water can be reused after that, after the removal of the toxic contaminants. Then we come to phosphorus removal. Phosphorus removal, again, phosphorus, for all of you to remember, phosphorus is highly insoluble. It combines with any cations that are present. So if you have calcium, if you have iron, it will precipitate. Now, that is why we can use alum as a coagulant in tertiary treatment and remove it from solution. But I would like to emphasize again and again that in many parts of our country and all over the world, in fact, for throughout history, perhaps for the last 5,000 to 10,000 years, wastewater has always been seen as a rich source of nutrients in agriculture. People spend enormous amounts of money for buying fertilizer, and therefore treated wastewater is a rich source of nitrogen and phosphorus, which can be used provided, and that's also very important, provided there are no other toxic contaminants. And those toxic contaminants can be heavy metals, they can be detergents. For example, in urban wastewater today, we have high detergent levels. If the level of detergent in the wastewater is high, that also will result in poor agricultural productivity. Plants do not tolerate detergent. So it's becoming more and more difficult to deal with wastewater treatment. So here you have two useful nutrients which need to be utilized, but you also have toxic contaminants like heavy metals and detergents which need to be removed. So that brings us to tertiary and advanced levels of treatment, which I'm not obviously going to have time to work on. We will not be able to cover that, and maybe I will cover it in advanced wastewater treatment, which I do to some extent. Okay, so this brings me to the end of wastewater treatment. So this is the end of water and wastewater treatment. A couple of practice problems are noted on this slide. I may add some others at a later time, and I will end this topic right here. Thank you.